All right, today we're jumping into a huge question, one you hear all the time. What is really driving climate change? We're going to break down the science here, looking at everything from the planet's ancient, super slow rhythms to, well, our own much more recent impact. Let's get right into it.
So, you've probably heard this one, right? The climate's always been changing. And you know what? It's a fantastic question because it's absolutely true. Earth's climate has never, ever been static. But, and this is the key, to really get what's happening now, we've got to understand the difference between different kinds of change, their causes, and honestly, the speed. Let's start by getting some perspective. Just take a look at this timeline. The Earth, it's been around for an incredible 4.5 billion years. And humanity? Well, our ancestors started using the most basic stone tools just 300,000 years ago. In geological time, that's not even a blink of an eye. And that context is so important because it tells us that for almost its entire history, the climate changed completely on its own. So what was making it change?
Well, that brings us right to part one, the Earth's natural rhythms. We're talking about the powerful, deep time forces that have been running the show on this planet for eons. Okay, so what I love about this is the contrast. You've got two major natural drivers that are just operating on completely different clocks. On one hand, you have these incredibly slow, predictable cycles. They're called Milankovitch cycles, and they're what push the planet in and out of ice ages over tens and tens of thousands of years. And on the other hand, you've got these really sudden, dramatic volcanic eruptions that can cool the entire globe, but only for a few years. Slow and steady versus fast and furious.
Let's zoom in on those Milankovitch cycles for a second. They're basically a combo of three little orbital tweaks. First, the shape of Earth's path around the sun. It shifts from being more circular to a bit more oval-shaped on a 100,000-year cycle. Then, the angle of the Earth's tilt, what gives us our seasons. It changes over about 40,000 years. And finally, there's the subtle little wobble on its axis, kind of like a spinning top. Put all those together, and they decide how much solar energy different parts of the planet get over very long periods. And that's what drives those big ice age cycles.
But that leads to a pretty logical question, right? If the Earth's orbit matters because it changes how we get the sun's energy, what about the sun itself? Doesn't its own power change? It's a great question. And yes, it does. But the recent data tells a pretty surprising story. So here's the kicker. The sun does have its own cycles. It gets a little brighter and a little dimmer. But according to satellite measurements we've had since the 1970s, its overall energy output has actually been on a slight downward trend. Now think about that. During that exact same period, global temperatures have been shooting up. The two trends are literally moving in opposite directions. So that pretty much rules out the sun as the cause for our current warming.
Okay, so let's switch gears and go back to that other natural driver, volcanoes. They're amazing because they give us this perfect real-world experiment for how fast the atmosphere can change. And the 1991 eruption of Mount Pinatubo, it's the perfect case study.
I mean, just try to wrap your head around this. This eruption wasn't just some smoke and ash. It was so violent that it blasted 20 million tons of sulfur dioxide way up into the stratosphere, far above any weather or clouds. Once it was up there, that gas mixed with water and formed this global haze of tiny reflective particles. And here's the result. That hazy layer basically acted like a giant, temporary sunshade for the entire planet. It reflected sunlight back into space before it even had a chance to warm us up. And the effect was clear as day. Global average temperatures dropped by about 0.5 degrees Celsius for the next 2 years. It was a huge, but temporary, cooling effect, which, you'll notice, is the exact opposite of what we're experiencing now. And that brings us right to part two, the human factor. We've seen the planet's natural rhythms, these long, slow dances. Now, let's see where we fit into the picture. And, more importantly, how fast our impact is happening.
Okay, first things first, we have to talk about the greenhouse effect. And it is so important to remember that this is a totally natural and totally essential process. Think of these gases as a blanket for the planet. They trap just enough of the sun's heat to make life possible. Seriously, without them, the average temperature on Earth would be a crazy -18 Celsius. So the greenhouse effect itself isn't the problem. The problem is how fast we're changing it.
And this quote from our source material really just nails it. It says that human actions are adding excess carbon dioxide, which is intensifying the whole process. We're essentially making that natural blanket thicker and thicker, trapping way more heat than the system is used to.
So where is all this extra stuff coming from? Well, the science really points to three main buckets of human activity: burning fossil fuels for our energy, all the deforestation that's happening, and certain kinds of agriculture.
Let's dig into fossil fuels for a second. I mean, what are we actually burning? Well, it's basically ancient sunlight. It's concentrated carbon that was captured by plants and little ocean critters hundreds of millions of years ago. It took eons for all that carbon to get buried and locked away deep underground, and we're digging it up and releasing it all back into the atmosphere in just a couple of centuries. The timescale is just staggering. Now, deforestation. This is like a 1-2 punch for the climate. First, when you cut down massive forests, you're getting rid of a giant natural sponge that sucks CO2 right out of the air. And second, what often happens next, that wood is burned to clear the land, say for cattle ranching, and all the carbon that was stored in those trees for decades or centuries gets released pretty much instantly.
And that brings us to another really important gas, and that's methane. You know, CO2 gets all the headlines, but methane is a super potent greenhouse gas too. And when it comes to agriculture, the two biggest sources are livestock, we're talking mainly about burps from cattle, and the bacteria that just love to grow in all those flooded rice paddies around the world.
And here's why scientists pay so much attention to methane. Look at this number. Molecule for molecule, it is roughly 25 times more powerful at trapping heat than carbon dioxide is. So even though there's a lot less of it up there, its warming punch is incredibly significant. Okay, we have covered a ton of ground here, from the wobble of the planet all the way to modern farming. So let's head into our final section, part 3, and really put all these pieces together. This table right here, this is what pulls the whole story together. Look at the natural drivers. You've got orbital cycles, which cause warming and cooling, but on a timescale of tens of thousands of years. Then you have volcanoes, which cause cooling, but it's super short term, right? Just a couple of years. Now look at the human drivers. They are causing persistent, long-term warming on a timescale of just decades to centuries. It's the speed. The speed is what's completely out of whack with the planet's natural rhythms. So that leaves us with this final question. We started with the climate has always changed, and we've seen that's true. But now that we understand the profound difference between those slow natural cycles and this new, rapid, human-driven warming, how does that change our perspective? How does it frame the way we think about the future? It's definitely something to think about. Thanks for joining me.